So welcome to another week of Level 1 NCEA Mechanics in Review. This week we're looking at Section 2 of the course, which is all about forces. Section 1 was covering acceleration and velocity time graphs and distance time graphs. So Section 2 looks at forces. We're going to look at Newton's laws of motion. Now, they're not really explicitly mentioned in NCEA Level 1 physics, but the concepts are assessed, so we'll talk about these three laws. Number 2, we look at labeling forces and the net force concept. And then number 3, we'll introduce some new formulae here. We'll introduce force equals mass times acceleration, which can also be reiterated as weight equals mass times gravity. And then the fourth factor we look at today will be pressure equals force over area. The context for these is probably best to just look at some exam questions, and then we'll illustrate the points as we go. So if we just lay down Newton's three laws of motion, first of all, before we get started with any exam questions. So Newton's laws of motion. So Isaac Newton came up with these three laws of motion, and the first law states that an object will keep doing what it's doing. Just write this out and then record. Okay, so I've just written that out to save some time. So Newton's first law of motion, an object will keep doing what it's doing unless the forces acting on it become unbalanced. So we'll take a look at a question from 2013. And this question looks at the scenario of a runner, and the graph, the velocity time graph, I've just reproduced it right here on the page beside it. And in this case, they're assessing the concept of Newton's first law of motion, the idea of forces being balanced or unbalanced. So the question reads, on the diagram below, these three diagrams from section A, B, and C of the velocity time graph, draw and label the thrust and friction forces acting on the runner. In your answer, you should use arrows to show the directions of thrust and friction forces. Beside each diagram, state if thrust is greater than friction, thrust is equal to friction, or thrust is less than friction. So this is all based on Newton's first law, whether forces are balanced or unbalanced. So if we look at the first picture here, section A on the graph, on a velocity time graph, this means acceleration. So you have acceleration there. Section B would be constant speed. And then section C would be deceleration or negative acceleration. So if we go to our diagram, then the forces, the thrust force is what is acting in this direction. So this would be thrust. And since in section A the runner is accelerating, the friction force should be smaller than your thrust force. So they said use arrows to show the direction. So we did that, and then state that thrust is greater than friction. So in this case, thrust is greater than friction. Forces are unbalanced. Forces are unbalanced, and therefore you get acceleration, which is a change in motion. So that follows Newton's first law. If we take a look at the second picture, section B, we're moving at constant speed here. Constant speed means the forces are balanced, so the forces of thrust and friction in this case. To show that balance in the forces, we want to draw force arrows which are the same in size. So in this case, thrust is equal to friction. Thrust force is equal to friction. The forces are balanced. Forces are balanced, and therefore you have constant speed, which means no change in motion. So the object keeps doing what it's doing because there's no unbalancing in the forces. And section C, then we have deceleration, in which case the thrust force is still there, but the friction force is now larger. And so thrust is now less than friction. And we have forces are unbalanced again, so we have a change in motion. Forces are unbalanced, and therefore we get deceleration. Yeah, that would be the answer to that first part. That's part A. Now, part B of the question is just above the graph here, so we'll take a look at that. It continues, or part C rather. That was part B. Part C. Referring to your force diagrams in part B, explain the link between the net force acting on the runner in sections A, B, and C of the graph and the type of motion. In your answer, you should describe what is meant by net force, explain the link between net force and the motion for each section, and compare the direction of the net force and the direction of the motion for each section. Okay, so the easiest way to explain what net force is to actually just add some values to the forces. So in the first section here, we said that the thrust force was greater than the friction. So if we give those some values, if we say the thrust force is equal to 50 newtons, and then the friction force is less than that, so let's say it's 30 newtons, then the net force, or F net, is going to be 20 newtons, so 50 minus 30, and it's going to be in the forwards direction. If we look at the second situation, the forces are balanced, so we could say that we have now got 50 newtons of thrust again, but we also have 50 newtons of friction. So in this case, the forces are now balanced. The F net is equal to 0 newton, and therefore there is no change in motion, so that's the 0 net force. And in the last picture then, we're looking at the fact that friction is greater than thrust. So let's say friction is equal to 60 newtons here, and then the thrust force forward is only 30 newtons, and therefore the F net in this case is going to be equal to 30 newtons, and that's going to be in the backwards direction. So net force is just when you look at all the forces acting on the object and you add them all up and look at what the surplus force is, it's going to be acting in one particular direction. You could also consider support and gravity here, but since they're balanced the whole time, so if say they were 40 newtons for support and 40 newtons for gravity, well, they effectively cancel each other out there in all cases, so 40 and 40. So that's what net force is. Now, if we go back up and look at what else the question is asking us, they asked us to explain the link between net force and the motion for each section, which I effectively did, and compare the direction of the net force and the direction of the motion for each section, which we just looked at as well. For a more detailed answer, here's what the NCEA answer looks like. So net force is the resultant force, and net force is also referred to as resultant force when multiple forces interact. The multiple forces we had here were friction, gravity. We also had support force there, which is just a surface supporting an object. And then we also had thrust. So when multiple forces interact, if the forces are pointing in the same direction, the forces add, giving a larger net force. So if we look back at our exam question for a second, just to exemplify that, you could have friction from the surface of the ground. So just redraw this for a second. This is your runner. You're going to have support force of the ground as it supports that object. But you can also have friction, which is between two surfaces in contact. And then let's say the wind picks up, the headwind picks up, there's going to be an increase in air resistance. So air resistance up here. And if those two forces are acting in the same direction, which they are, then the 20 newtons from air resistance, so the 30 newtons from friction on the surface will add to give an additional net force there. The thrust, let's say, was 40 newtons. So thrust is 40 newtons, and the air resistance plus friction makes 50 newtons, then the F net in that case is going to be 10 newtons in the backwards direction. So that's what they mean by net forces being additive. So if the forces are in opposite directions, the forces subtract, giving a smaller net force, including a zero net force. Net forces determine whether the runner is accelerating, decelerating, or maintaining a constant speed. Accelerating was section A, decelerating was section C, and maintaining a constant speed was section B. If the net force is pointing the same direction as the direction of motion, the object accelerates. If the net force is pointing the opposite direction to the direction of motion, the object decelerates. And if there is zero net force, then the object maintains a constant speed or is stationary. And so in section A, the runner is accelerating. This is because there is a net force pointing forwards. This occurs when the thrust force is greater than the friction. Section B, the runner has a constant speed. This is because there is no overall net force. This occurs when the thrust force is equal to friction. And in section C, the runner is decelerating. This is because there is a net force pointing in the opposite direction to the motion. So you do need to be aware that when you're answering these questions, you need to write as full a detailed answer as possible. What I did was quite short, just using some diagrams. You need to write the text to support your answer. But that's, we go back to our objectives for today's video. We've looked at Newton's first law of motion. We've looked at labeling forces and the net force concept. So we're going to now take a look at Newton's second law, which is about force and mass applied. force, mass, and acceleration. So let's take a look at section 3 now. Okay, so moving on to Newton's second law. Newton's second law of motion says that the acceleration of an object is due to the force and mass applied, which is essentially force equals mass times acceleration. So F equals force. Forces are all measured in newtons. Mass has to be in kilograms. Just remember that. So if you have something in grams, convert to kilograms. And acceleration, as we had in section 1, is in meters per second squared. It's a very straightforward formula to use. You just have to be able to recognize where it appears in exam questions. So if we take a look at 2011, we have a question about a runner again. And there are two sections that we're looking at here, section X and section Y. A boy runs along a track as shown above. During section X, he runs with a constant speed of 2 meters per second for 15 seconds. During section Y, he runs with a constant acceleration of 0.2 meters per second squared. Calculate the net force acting on the boy with a mass of 60 kilograms during section Y, and give an appropriate unit for your answer. So it's simply using F equals m times a, force equals mass times acceleration, where this is F net that we're looking at. And that's going to be equal to 60 kilograms multiplied by 0.2 meters per second squared, which works out to be an answer of 12 newtons. So that's how you use force equals mass times acceleration. Now, sometimes they may ask you to rearrange the formula. So if you had to do a formula triangle for that, you would have force on the top, because force equals mass times acceleration. So force equals mass times acceleration, F on the top, m on the bottom, multiplied by a. So if you want to work out the acceleration in this case, given the force, you would say cover the one that you're looking for. So we would cover a in this case, and we're looking for acceleration is going to be equal to force divided by mass, which in this case would be 12 newtons divided by 60 kilograms, and that should give you your 0.2 meters per second squared. So you need to remember how to turn the formula force equals mass times acceleration into this triangle. But that's essentially what you can come across with force equals mass times acceleration. The other relationship is between weight, mass, and gravity, which is essentially the same formula. So we'll take a look at an example of one of those questions. Okay, so this is question 3 from 2013. And in this case, we're looking at the difference between weight and mass, and then we're calculating the weight of a box. A box in a warehouse has a mass of 2,500 kilograms, so it's in kgs already, nothing to worry about there. Let's weigh the difference between weight and mass. It's not often on the physics papers they get you to explain concepts, but in this case you do. So weight and mass, the weight of an object is the force that it exerts on a surface, the force that it exerts or applies on a surface due to gravity pulling down on it. So weight is a force, and therefore it's measured in newtons, not kilograms. So weight of an object, the weight of an object is the force that it exerts on a surface due to gravity pulling down it, whereas the mass is the amount of matter in something, the amount of matter in an object, and this is measured in kilograms. Now, the great way to explain this is if you have a mass of 60 kgs on Earth, then your mass on the moon will also be 60 kgs, because you don't, unless you remove part of your body, chop an arm off or a foot or whatever, you're going to have the same amount of matter making you up. So you should have the same mass, 60 kilograms. However, your weight is different. Your weight on Earth would be 600 newtons, and your weight on the moon would be a sixth of that there, so you'd only be 100 newtons. And that's because gravity on the moon is a sixth less. Gravity is 6 times less powerful on the moon than it is on the Earth, and that's due to the fact that the moon is much smaller. So it's your weight that changes as you move throughout the solar system, not your mass. And that's the difference there. If we look at the NCEA answer for that one, Weight is the downward force due to gravity that an object experiences, while mass is a measure of amount of matter that an object has. Back to the question. They want you to calculate the weight of a box. Now, the weight formula is equal to mass times gravity. This is essentially a reiteration of the force equals mass times acceleration formula, because the value of g is still 10, mass is still in kilograms, and weight is still in newtons. So they're effectively the same formulas. The value of g, though, we're looking at here is actually the force due to gravity, which is 10 newtons per kilogram in this formula, whereas in this formula here, it's acceleration due to gravity, which is 10 meters per second squared. So the units just change, but effectively it's the same number. So the weight of the box here, weight of the box is going to be equal to the mass, which was 2,500 kilograms, and that was given up top here. So 2,500 kilograms by gravity, which is 10 newtons per kilogram, and that will get rid of your kgs there, which will give you an answer of 25,000 newtons, and that's the weight of the box in newtons. So that's the W equals M times G formula. So the last thing we want to look at this morning is the pressure equals force over area formula. So P stands for pressure, and that's going to be newtons per meter squared, because we have force, which is measured in newtons, being divided by area, which in this case is being measured in meters squared. So pressure equals force over area. You get a formula essentially to calculate the pressure exerted by an object, and then you usually have to explain the concept of surface area and the spreading of pressure. Okay, so for the final section where we're looking at pressure equals force over area, we're looking at this question 4 from 2011. And question 4 from 2011 was about a pair of football boots, one pair with studs and one pair without studs. The question is as follows. A student of mass 40 kilograms uses the football boots shown above. One boot without studs has a surface area of 165 centimeters squared, which is, if you divide that by 100, that's 0.0165 meters squared in contact with the ground. One boot with 6 studs has a surface area of only 6 centimeters squared, or 0.0006 meters squared in contact with the ground. So this surface area here is much smaller than the surface area above if you don't have the studs. Calculate the pressure, P, exerted if the student stands on 1 foot. Now the significance of saying 1 foot is that you only have to do the calculation for 1 foot. If it was both feet, then you'd have to times the surface area by 2. On a hard surface for the boot without studs and for the boot with studs. So without studs, the pressure equals force over area. Now the force of the student is going to be worked out using force equals mass times G, which in this case we're using the weight formula, so W equals M times G. So that's equal to 40 kilograms multiplied by the force of gravity, which we just had was 10 newtons per kilogram. And that gives you a value of 400 newtons for the weight of this student. So the weight of this student is going to be constant in this case. So the pressure is going to be equal to 400 newtons divided by the area, in this case in meters squared, which is 0.0165 meters squared. And that gives you a pressure for the boot without studs of 24,242 newtons per meter squared. So that's the answer that would go there. And then with studs, pressure is equal to force over area. So in this case, it's 400 newtons, and that's being exerted over a surface area which is much smaller, of only 0.006 meters squared. And that gives you a pressure of 666,667 newtons per meter squared. So the pressure is much greater with the studs than without the studs. And then the question goes on and says, what is the advantage of having studs? So discuss the advantage gained by the student when running on soft grass football field while wearing the boots with studs compared with wearing the boots of the same size without studs. in your answer, you should compare the pressure exerted on the ground by the boot with the studs and the boot without the studs. So with the studs, we just had the pressure was 666,667 newtons per meter squared. And then the boot without the studs, we just had the pressure was equal to 24,242 newtons per meter squared. And then explain the relationship between surface area and the pressure exerted, and explain how the difference in pressures would help a student run on a softer surface like grass. So effectively, because the pressure is much, much higher on the boot with the studs, the boot is going to push those studs into the soft grass, and then you get better traction. And then for the boot without the studs, the pressure is much less, and as a result, the boot isn't going to really grip the surface, and therefore you won't have much traction to run around and play football. If we look at the answer from NCEA on that one, they say for 2011, excuse me, 2011 we're looking at. Here's the comparison. I'll just zoom in a bit. Okay, so the pressure exerted by the boot with studs is greater than the boot without studs. We just looked at that with the two values right there. The smaller the surface area, which is the force which the force is exerted over, the greater the pressure exerted on the ground. How it helps in grass: as the student's weight is applied over a smaller surface area with the boots with studs, it leads to a greater pressure on the ground. This means that the studs will sink into the ground more, which will enable the student to get a better grip or traction on the grass when running. Now this question comes up every year. It's just that they change the context. Sometimes it's skis on snow, sometimes it's snowshoes on snow. In this case, it was football boots on grass, and all they do is change the context from year to year. But that is a review of all the teaching I've done this week and a little bit into next week. It's all about section 2 forces, and then after we come back from the holidays, we look at the final section for level 1 mechanics, which will be on energy changes.